Hi everyone, and welcome to the final lecture in this mini course of Gopakumar-Vafa Invariant. It has been an amazing set of lectures, and now finishing with this talk on Gopakumar-Vafa Invariants via Perverse Sheaves. Yukinobu Toda, please go ahead.
Yes, thank you very much. So today finally I will talk about the Gopakumar-Vafa invariants, but I have to explain one more thing before that. So I said that yes, I first start with cohomological DT theory. So I wanted to define energy beta, and we need some. I said that we need some cohomology theory on the moduli space of the stable Sheaves. So need some cohomology theory. So this cohomology theory, the so-called cohomological Donaldson-Thomas theory, plays a key role about constructing such cohomology theory. So there I first give a overview about this theory. Let's recall that for Calabian C for the X, I have defined the Donaldson-Thomas invariant. So this is defined as certain integration of the virtual class, at least when the moduli space is fine. For example, when the numerical class is primitive and the ample class is generic or something like that. In that case, there is no strict semi-stable Sheaves, and the resulting DT invariant was integer. So otherwise, there is also generalized Donaldson-Thomas invariant. So that was given by Joyce and Son. So in general, it is a rational number, but in the fine case, this is in fact integer. And in fact, in this case, we have two ways to define it. The first way was it was defined to be the degree of the zero-dimensional virtual class. And the second one is weighted Euler characteristic of variant constructive function. And the second construction gives a way to define this invariant into some motivic or cohomological level. And today I talk about its cohomological refinement of this one. This means that, for example, if M is smooth, then as I explained, either in this computation we can see that the DT invariant is nothing but the weighted Euler, nothing but the usual Euler number of the moduli space up to sign. So then, of course, this Euler number can be recovered from the cohomology of the moduli space. So this is a graded vector space. This graded vector space recovers this Euler characteristic by taking the alternating sum of its dimensions. So the idea of cohomological Donaldson-Thomas invariant is considering not the Euler number, but consider cohomology of the moduli space. So from this observation, it is natural to define the Donaldson-Thomas invariant to a graded vector space. So the Donaldson-Thomas invariant was, this is an integer, and there is from the graded vector space to integer. If it is finite dimensional, you can recover some integer by taking its Euler number. And the idea of the cohomological Donaldson-Thomas invariant is to find some graded vector space which recovers the Donaldson-Thomas invariant by taking its Euler characteristic. Such a construction was proposed first by Konsmich-Sabelman, and its mathematical rigorous validation was given by Joyce and his collaborators. It was about 2012, something like that. The point is to construct some perverse sheaf on this moduli space. This is now called DT perverse sheaf. And this DT perverse sheaf is the key to define the Gopakumar-Vafa invariant. But so far, this construction of DT perverse sheaf requires more refined moduli space, like derived moduli space and shifted symplectic structure. So in this lecture, I make it as a black box, and I just give what is the classical shadow, which is deduced from such refined structure on this moduli space. But before that, I have to also explain about the perverse sheaf, because so far I considered only the derived category of coherent sheaves. so far considered only derived category of quotient sheaves, but because that the derived category can be defined for any abelian category. And the perverse sheaf is not object in the derived category of quotient sheaves, but derived category of constructive sheaves, not quotient sheaves. For example, for a topological space M, the constant sheaf is a constructive sheaf, but not this is a constructive sheaf, but not coherent sheaf. So, roughly speaking, the constructive sheaf is something more topological data, and coherent sheaf is something algebraic geometry data. More generally, if for example, if there is a representation of the fundamental group of M, then there is associated locally constant sheaf. That is also a constructive sheaf. And if you take some push forward, pull back of constructive sheaf by or some continuous map, then this is also a constructive sheaf. More generally, a constructive sheaf, a sheaf F on some topological space is constructive if there is a decomposition M into some strata such that the sheaf is locally constant at each strata. For example, in the case of M is just a fine line, so there might be some, say, M is just C. So then there might be some point such that this sheaf is constant except these points, but some stocks may jump at each point. So then so this is now abelian category, and similar to before, I define the BM to be the bounded derived category of constructive sheaves on M, and with Q coefficient. Then the power sheaf is defined to be some object in the derived category of power of constructive sheaves. So this is the formal definition of power sheaves. So that is, this is power sheaf if for all I, if you consider cohomology of this complex, then the dimension of the support of the i's cohomology has less than or equal to minus I, and similarly it happens after applying the derived dual of this sheaf E. That is, for the first condition, it means that so there is no cohomology in the positive degree, and the cohomology happens degree 0, -1, -2, so on. For degree 0, the dimension of the support is this is 0-dimensional for H minus E. So this is either 0-dimensional or 1-dimensional. And similarly, H minus E, so this is 0-dimensional, one-dimensional or 2-dimensional, and so this and this holds for arbitrary negative degree, and then this also holds after applying this dualizing functor. So this dualizing functor is given by this one. So this is the dual with respect to this dualizing sheaf. So this is called dualizing functor. The point of this definition of the power sheaf is that from this definition, is the power sheaf if and only if. So this is power sheaf if and only if the derived dual is also perverse. And the important fact about power sheaf is that so this is a subcategory of the derived category of constructive sheaves, but this is in fact heart of T structure. The notion of heart of T structure was explained in the second lecture, and this is in fact abelian category. So this means that this is in fact abelian category. So this is quite important abelian category in the bounded derived category of constructive sheaves. And that also plays a role in the so-called Riemann-Hilbert correspondence. So the so-called by the Riemann-Hilbert correspondence, that this category corresponds to the regular phonomic D modules. So this is very important in several aspects of mathematics. Here is some simple example of perverse sheaves. So this is, let's have a local system on M. So this means that locally constant sheaf. So this one corresponds to the representation of the fundamental group. So given representation power M, so there is associated local system where the monodrome is given by this representation. Then this shift L shift by dimension M. This is perverse shift. So this is from the definition. This is because the this of course this satisfies the first condition of the perverse shift, and because this is local system, if you apply this derived dual, then this is equal to L dual of the dimension M, and L dual is again a local system. So this is this satisfies the condition of the perverse shift. So yeah, so obviously this is a perverse shift. And similarly, if you take the closed immersion, then also say that is also smooth. And then for a local system, then it's push forward, but shift by dimension z is also again a perverse shift. Of course, when z equals just m, so this is just the first example. And so the second example means that there is also something similar for closed subset. And also, so this is the case where we have only one cohomology. But by taking some extension of this object, we can also construct object with several non-trivial homologies. For example, let's take OP immersion from C star to A1. So then let's take the push forward of the constant sheaf with Q coefficient by J. So then, so this is the object of the derived category of constructive sheaves. But so this is embedding after removing the origin, and the stock of this complex, the stock of the complex at the origin 0 is computed by the cohomology of this this space. That is it is motorically equivalent to S1. So the stock of this one can be computed by the cohomology of S1, which is just Q and Q by -1. So then from this one, we obtain this distinguished triangle. This is not, this means that the, so this one is perverse from the first example. So this is perv, and this is the perverse in the first example. And because the perverse shift is out of T structure, it is closed on the extensions. So by this is also like lives in perverse shifts. So in this way, so we can construct several examples of perverse shifts. But the most important maybe example of the perverse shift are given by so-called vanishing cycles or nearby cycles. So let me give a smooth scheme. And f is some regular function on it. And for simplicity, I assume that the critical locus of f, let's recall that the critical locus is the zero locus of the vanishing locus of the drum differential of f. And let's assume that this is theoretically contained in f inverse 0. So in this setting, we can, there are some associated factors by f and psi s. Phi f and psi s. So this is phi f is called vanishing cycle factor, and psi f is called nearby cycle factor. I will in the next slide I will explain its construction. But But in particular, applying it for this constant sheaf shifted by dimension V. Let's recall that in the previous slide, it was the object of the perverse sheaf. So then by applying this vanishing cycle factor, we obtain other vanishing cycle, other perverse sheaf on the zero locus of this function f. So this is called also called vanishing cycle sheaf. And the special property of this vanishing cycle sheaf is that this sheaf is in fact supported on the critical locus. So a priori, so this is the perverse sheaf on V0, but if you apply this special object, then it can be shown that this is supported on this critical locus, and in fact, so this is the object of the perverse sheaf of the critical locus. Here is some detail about how to construct vanishing cycles. So these are defined in the following way. Let's take a universal covering space of C star. We can take the exponential map from C to C star. So this is the universal covering space. So then the setting is starting from this one, and the fiber is given by this V0. And then I take the fiber product and the fiber product. So this is V0 is just a pre-image of F under this system. So this is the locus where the F is non-zero. And then I take the pull back to the universal covering space. And then I get this diagram. And then I also define J to be this composition. Then the definition of the nearby cycle factor is that from the shift F, I take the pull back and then push forward and then restrict to here. So this is the definition of the nearby cycle. But for conventional reason, I take shift by -1. This shift by -1 is required in order to make sure that this is in fact perverse shift. So this is something like the considering the some sort of given a shift F. This is something looking at some generic the generic fiber of this restriction of this shift to the some sort of generic fiber of this F. And then restrict it to here. This means that for each point, we take some sort of open neighborhood and then restrict shift V to some nearby fiber of some open neighborhood at this point V0. So something similar was already appeared in the previous lecture. So we consider some Milner fiber. So this is very similar constructions. And in fact, so this nearby cycle is closely related to the Milner fibers. And then the vanishing cycle factor is defined so that there is some canonical map from I star F to I star J star Kappa star F. So this is nothing but the junction because J lower star is this is a right adjoint factor of the J upper star. So there is a canonical map from identity factor to here. So then just by applying I upper star, I get this canonical map. And then applying also by shift -1, I get a canonical map from here to here. And then take the cone of this map. So this is the definition of the vanishing cycle factor. So here are some examples of the computation of the vanishing cycles. Let V be just a one-dimensional fine line, and let's take f to be the function, t to the n plus 1. So in this case, the critical locus of this function f is, of course, spec cd over the n. So this is just the derivation of z, the power of d by z. And then the Yes, so so this is this means that phi f applied to Q of Q1 is just this one. So this is because we have this function C to C set to n plus 1, and then applying here. But the 5 of this map is just n plus 1 point. So then applying the nearby cycle factor, we get that just Q0 plus n plus 1. So this is the nearby cycle sheaf. And then I take the cone over this one. Then I get this n-dimensional vector space as a vanishing cycle of this function. So similarly, so this case is less trivial, but let's take V to be the two-dimensional affine space, and let's take F to be this function. Then the critical locus is, of course, given in this way. So this is so this part is the xf, and this y is the yf. And geometrically, so this critical locus looks like just a1. At least set theoretically. So this is the locus where xy equals 0 and x squared equals 0. Set theoretically, so this is just x equals 0. Set theoretically, so this is just x equals 0. But this is not isomorphic to A1 because there is some non-reduced scheme structure on here. And in this case, the vanishing cycle, the stroke of the vanishing cycle shift depends on which point you take on this A1. And in fact, vanishing cycle is just a constant shift, except origin, but at the origin, so this is some non-trivial power shift. That is, the zeroth cohomology is in fact calculated as in this way, where V is the kernel of this. So there is exact sequence like 0 to V2, QA1 to Q0. We can also write it as extension like Q0 to V shift by 1 to QA shift by 1. And the H1 of this vanishing cycle is just Q0. So this means that the vanishing cycle is in fact has this distinct triangle. And again, so this is also distinct triangle. So this means that this vanishing cycle is generated by Q0 and also QA1 shift by 1. And so in fact, so this is a self-dual, so that after dual we get the opposite the filtration, but the resulting filtration is the same. So in this way, we can obtain some non-trivial example of the vanishing cycle shift. So then again, so this vanishing cycle shift is closely related to the variant functions. So in fact, so this is the variant function is nothing but the pointwise Euler characteristic of the vanishing cycle shift. For each homomorphic function f, from the definition of the vanishing cycle shifts, we have this relationship. So this follows immediately from the definition of the vanishing cycles. That is in fact, so this term appears as so let's recall that we have this the -1 to psi f to phi f. So we have this one. And yes, now if we want to take f to be qv dimension v. So then this term appears as Euler characteristic of this term. And this term appears as Euler characteristic of this nearby cycles. So then we have this interpretation of the Euler number of the mu interpretation of the variant function in terms of the Euler number of the vanishing cycle sheaf. So this is that is if we consider variant function of the critical locus, then this is equal to the pointwise Euler number of the vanishing cycle complex. So then from this observation, now this is a power sheaf on this critical locus. So it makes sense to consider its hypercohomology. Or more precisely, this is just the cohomology of the push forward. We have the map from here to here, and then we take the push forward functor of the vanishing cycle complex to here, and then take the cohomology. So then this makes sense as some graded vector space. In fact, this is finite dimensional vector space, finite dimensional graded vector space. And then by taking its Euler number, we obtain the weighted Euler characteristic of the variant function. So recall that this is a thing about k of E of chi inverse k. So this construction appeared as an alternative way to define Thomas invariant. And so this, in fact, this is a local contribution of the Thomas invariant. That is, the modular space of stable sheaves is locally as critical locus. And locally, the DT invariant can be obtained as the weighted Euler characteristic. So in this way, we have some sort of homological version of the local contribution of the Thomas invariant. Let me call that locally, the modular space of stable sheaves M on a curvature seafold is of this form, that is critical locus of some function. So there is some embedding to V and F. Then from this observation, this cohomology gives the local contribution of the Thomas invariant. But this is only the local construction, and it is natural to consider whether we can globalize these constructions. It is natural to try to globalize this cohomological refinement. And in fact, this description depends on a choice of point. So if you take defined point of this modular space, then we have defined choice of V and F. And it is not clear whether this construction good to give a global homology theory. And in fact, it is enough to consider some global power sheaf, which locally gives this vanishing cycle complex. We want to construct some global power sheaf such that its hypercohomology recovers the original Thomas invariant. So then we need to know. So then, in order to glue it, let's say we have this modular space of stable sheaves, and we have this U and U prime. So locally, we know how to give us the cohomological refinement of DT invariant by vanishing cycle complex. So the question is that how these interact on the overlaps of each open subset. In order to answer this, we need some more defined structure on this modular space. This is now called the D-critical structure. So this notion was introduced by Joyce in order to obtain such a global information of how to glue the vanishing cycle complex. And this is regarded as some sort of the classical shadow of minus one shaded symplectic structure in derived algebraic geometry. So this is given by a global section of some sheaf of C vector spaces over M. So this is some sheaf canonically defined on each scheme M, which I'm going to explain. For each complex scheme M, there is a canonical sheaf of C vector spaces, M, satisfying the following properties. For any open subset U and also closed embedding in V, for smooth scheme V, so then there is associated exact sequence. That is, we define this sheaf S on U just by the kernel of this map. The point is that the description of OV, I, and omega V, so it depends on a choice of this embedding. But nevertheless, this sheaf is independent of the choice of these choices. So in this way, the locally defined sheaf SM can be canonically good to give a global sheaf of C vector space. So that was proven in Joyce's paper. And in fact, this sheaf is related to the cotangent complex of the sheaf M, so that it is an intrinsic one to each scheme. And technically, we also take the decomposition CM0 plus CM because the constant sheaf always lies in the kernel of this map. And then there is some decomposition into the constant function and the other one. So here is the definition of D critical structure. So the definition is that pair of M and S, M is a C scheme, and S is a global section of the canonical sheaf SM0 in the previous slide. So this pair is called D critical locus if it is covered by open subsets U satisfying the following conditions. The first condition is that there is a closed immersion U inside into some smooth scheme Y, and also some function F such that U is given by critical locus. So if a D critical locus is given, so it is written by a critical locus of some function. So this is the first definition, but the point of this definition is that how this function interact globally. So this is the second condition. That is, so if you take the S restriction of S to each open subset U, then this is given by this function F modulo the df square. So this df square is that in the previous slide, this one is given by the kernel of OV, kernel of OY and I square to one differential of omega y over I omega y. But now I is given by generated by the differential of F. So then from this definition, the function F is tautologically, this is the kernel of this map. So F is in fact lives in here. So this definition implies that the locally defined function F can be globalized as a global section of some sheaf of C vector space. So then the data of U, so this is open subset, and embedding and function and I, so this is called D critical chart. So this is the definition of D critical structure. And then it is important to see what this D critical structure gives some global information. Or as a local consequence of D critical locus is that locally, so this is given by critical locus. But it says something more about some global structures. So if there are two D critical charts, you say for a given open subset U, let's say we have this Y1 and Y2. Then analytic locally, they are related by this by this. That is, Y2 is basically, essentially Y2 is given by the Y1 product some affine space. And this function F2 is given if the difference of the function F2 and F1 are given just by some quadratic form, non-degenerate quadratic form Q. So of course, in this case, we have the isomorphism of the critical locus. And also we have the isomorphism of the vanishing cycles. So this is so-called Thomas-Svechiani theorem. So there is so-called Thomas-Svechiani theorem for the vanishing cycle complex. And also it is easy to see that the vanishing cycle, yes, this is the special case in the previous example that this is in fact isomorphic to zero. So we see that at least analytic locally, we have the isomorphism of these vanishing cycles. This means that if we compare these vanishing cycles at the overlap of two open subsets, then there is some isomorphism. So then we may guess that it may be possible to group. However, the issue is that although we have this isomorphism, but this isomorphism is not canonical. So there are some choice of this isomorphism. And because of this non-canonicity, so it is not necessary to that this isomorphism can be grouped. So we have to choose some isomorphism so that it can be grouped. The so-called notion of orientation data was this was considered in order to cancel these ambiguities. That is, given 2D critical charts, U, Yj, Fj, Ij. So then the point is that we have some canonical isomorphism of the canonical line bundles. So this ky, I think so you also denoted as ky as omega y. This is because in the previous slide, I have this embedding and the omega, then ky2 is restricted to ky1 is isomorphic to ky1 tensor of the determinant of the conormal bundle. This is the conormal bundle. But this normal bundle can be trivialized. So this identification is equivalent to this one. And so this one is given by the quadratic form Q, given as before. At least if we restrict it to U, we have this canonical isomorphism. This indicates that so this locally defined canonical bundle tensor 2 can be canonically grouped to give some line bundle on each T critical locus. So there is some canonical line bundle on the critical locus, which is locally isomorphic to this one. So then the definition of orientation data is that, so this is a choice of square root line bundle of this one. So then given orientation data of M and S, and also for each D critical chart, so by the definition of this virtual canonical bundle of the D critical locus, then at each open subset of this D critical locus, we have this canonical isomorphisms. So then the orientation data is just square root of this line bundle. So then locally we can take the square root of these isomorphisms. So the choice of the square root of this isomorphism from a mu2 tensor over each open subset over the open subset U. So this gives some mu2 tensor, and then by taking push forward with the constant sheaf, we get some decomposition with a constant sheaf, with a push forward with a constant sheaf. And this is some rank 1 local system. So this rank 1 local system plays a role of gluing the locally defined power sheaves. So this is said by Joyce and his collaborators that for D critical locals with orientation data, then there is a power sheaf M, which is called DT power sheaf, such that for each D critical chart, we have this isomorphism. That is, locally we have this vanishing cycle complex, but after taking the tensor of this rank local system determined by orientation data, then we can glue these sheaves to get a global power sheaf. So that is the definition of that this is the construction of the DTT power sheaf. And in fact, that was the general story about the D critical structure. But in fact, if we consider modular space of fine modular space of stable sheaves, then there is a canonical D critical structure on it. So this is also the Joyce and his collaborators, like Bravo, Pushy, and Joyce. And here, so we have to use the -1 shifted symplectic structure in derived algebraic geometry, so which I didn't explain in this lecture. But this is some more defined structure on this modular space. And basically, so this is based on the observation that there is pairing x to 1, product x to 2 to complex numbers. So this is perfect pairing given by a series duality. So this is some sort of shifted duality. So, and the shifted symplectic structure is some refinement of this the data in derived algebraic geometry. Also, in this case, there is also orientation data. In this case, the virtual canonical line boundary is given by the determinant line boundary of the push forward of the universal sheaf. That is, at each point over the modular space, we consider determinant of the form of E. So this is the virtual canonical line boundary of this modular space coming from this D critical structure. And in fact, in this case, it is known that there are some orientation data. So then yes, now let M be the fine modular space. Yes, let's say this is fine modular space of stable sheaves. Then from the discussion so far, I have the associated DT power sheaf. But I should emphasize that, so this construction of DT power sheaf depends on a choice of orientation data. Which I will explain in some example. Anyway, the cohomological DT invariant is just given by the hypercohomology of this power sheaf. So this is a finite dimensional graded vector space. And in fact, it recovers the original Thomas invariant by taking the alternating sum of the dimension of this cohomological DT invariant. So here I give some example. So let's take C to be the some cubic curve inside P2, but singular cubic curve. In fact, this is a singular, and this is this normalization of this curve is just P1, and the geometry is that. So this is a rational nodal curve with one node P. And then let's take its one parameter deformation so that we take a smoothing of this rational nodal curve. So about the fiber, we get this singular curve, and the generic fiber is smooth elliptic curve. So this deformation is given by these equations. And then take a function that is t to t square. So t is the parameter of this one. So then if you take the critical locus m, then this is a d critical locus. Because this is, in fact, this is a globally, this is globally critical locus or something. So then it's the underlying set of this critical locus is nothing but this original curve C. So this is just C set theoretically. However, the scheme theoretically M is different from C. This is because by taking critical locus, there is some the non-reduced scheme structure on this node. The scheme structure, the non-reduced scheme structure at P is given by this equation. In fact, so this is the critical locus of this function u square v square. So by taking the derivative, I have this equation u square v equals u v square equals 0. But this is different from u v equals 0. And there is some embedded point at the origin. So in fact, so this D critical locus appears as some modular space of sheaves on Perverse fold. So for example, if you take this another rational curve, but embedded in some Perverse fold, so that this is embedded in some super rigid way, then the modular space of rank 1 torsion free sheaves supported on this curve is in fact isomorphic to this other scheme. And in this case, we can also calculate the virtual canonical bundle. So in fact, this is trivial line bundle. But the orientation data is a square root line bundle of this trivial bundle. And in fact, there are two choices of square root line bundles, because the in the nodal rational curve case, the degree 0 line bundles is just C star, and there are two choices of the square root of the trivial line boundary corresponding to plus minus 1 here. And the first one is, of course, a trivial line bundle. And the next one is there is some non-trivial line bundle, which is two torsion. That is L tensor 2 is isomorphic to C or C. So then the vanishing cycle complex also depends on the choice of each orientation data. And depending on this choice orientation data, so I omit this computation, but by the applying the previous definition, the resulting cohomological DT invariant is also dependent on choice of orientations. For the first orientation, this is given this way. That is there are degree -1 part, degree 0 part, and degree 1 part. This is the case where we have the trivial orientation. And in the other case, there's only homological degree 0 part. But of course, if you take the order characteristic of these graded vector spaces, they are the same. Because the order characteristic of this one is 3 minus 3 minus 1 minus 1, which is becomes 1. This is just 1. So the order characteristic of these graded vector spaces are the same, which requires the usual transformation invariant. But in general, the homological DT invariant depends on choice of orientation. So we have to be careful about this choice. So then now I'm going to explain about Gopakumar-Vafa invariant. So let's take to be a smooth projective Calabias fold. So we wanted to construct invariant ng beta for each non-negative G and beta is in homology class. From the modular space of one-dimensional stable sheaves of these Chan characters. So this is homology class coincides with B and KF equal 1. Well, maybe this is just the Chan 2 F. And this lies in H0 plus, H2 plus, H4 plus, H6. Then I'm now going to use the dt power C for M, which lives in here, to define the Gopakumar-Vafa invariants. So then I need one more step. So this is Hilbert-Chow map. For coherent sheaf whose support is one-dimensional, we can define its fundamental one cycle. So this is this also appeared in the previous lecture. So this is one cycle on X given by this formula. So eta is a scheme theoretic point, and this is a length. For example, if there is a curve C and on Calabrian seafold, and there are some Rankar vector bundle. So then I star F has, so this one has R times of this one cycle C. So this is keep track of the rank of the vector bundle over this curve C. So then we have the so-called Hilbert-Chow map. So this Chow beta is the modular space of effective one cycles. But we have to be careful about saying about modular space, about the Chow variety, because this is not something which represents some nice modular functor. So this is just a set theoretical modular space. So far we considered these modular space of stable shapes as some representing functors, so that it admits some nice obstruction theory. But so far, there's no nice obstruction theory on the Chow variety. So this is quite difficult part in dealing with the Chow variety. But anyway, after taking the reduced part of the modular space, so there is a map of schemes. So this is no. So this map is sending each sheaf to its fundamental one cycle. For example, if we take a point of a Chow variety where C is just a smooth curve without multiplicity, then the fiber of this map is so this is the set of sheaves whose support is it's just C with multiplicity 1. So this is nothing but the modular space of line bundles on this curve C. So it is isomorphic to the Jacobian C. But for example, so there might be some point where of C. And in this case, the fiber is much more complicated because it also contains ranked vector bundles on a curve. And also there also contains some sheaves which are somehow thickened sheaves, that is whose support is non-reduced. So this is some example of the Hilbert-Chow map. Let X be Calabrian seafold, which admits elliptic fibration F, and also with sections and integral fibers. So we have this elliptic fibration, but there are some singular fibers. And also there are sections. And also let's take beta to be the one cycle that corresponds to the half-time of the fiber class. So in that case, if the modular space of one-dimensional stable sheaves on X, so this is in fact isomorphic to X. So this is because over the generic fiber, this is isomorphic to the modular space of stable rank R and degree 1 vector bundles on elliptic curve. But this is not to be isomorphic to the elliptic curve itself. This is due to the result by Attia. And this can be globalized to give this isomorphism. But in this case, the child variety is bigger. So child variety is a symmetric product of that is. So the child variety is this is a one cycle correspond to like sigma of I of fi are some fibers. So and fi corresponds to some point over some point, fiber over some point, inverse pi. So then this one corresponds to the symmetric product of S by the pi is S, and we have the element of sigma of S. But the stability condition implies that every sheaf which corresponds to a point in M beta lives in only one fiber. Otherwise, it decomposes into the direct sum and it violates the stability condition. So then, in this case, the Hilbert chain map is just this condition that we have this isomoism, we have this map S, and then take the diagonal embedding. So then, let's recall that we have the dt power sheaf after fixing some orientations. Then I take its push forward to the chair variety to get some object in the derived category of constructive sheaves. And let's recall that the category of power sheaves on the chair variety. This is in fact, so this is a heart of T structure. So this means that there are some cohomological functors, which are denoted by PHI. So for each complex of constructive sheaves, then there is a cohomology functor with respect to the power T structure. So this is not the usual cohomology as a derived category of constructive sheaves. So this is a cohomology functor with respect to this power T structure. So then this is a definition of the Gopakumar-Vafa invariant. I define the invariant energy beta by this identity. So we call that M beta is modular space of one-dimensional stable sheaves, and I have this E beta chain map. The dt power sheaf lives in here. Then take its push forward, and then take ice perverse cohomology, and then take the Fourier characteristic of this one. So this is the alternating sum of the dimension of the hypercohomology of this power sheaf. And then take its generating sheet of this one. But from this definition, the left-hand side is in fact, so this is the Laurent polynomial. And in fact, this is invariant under this action. So this is nothing but the Bellier reality, that is. So this this one is in fact closed undertaking derived dual. So if we have a polynomial of y which is invariant under this transformations, then it is uniquely written as in the right-hand side for some unique choice of energy beta. So then this definition may make sense. And the meaning of this polynomial is, so this is in fact a Poincare polynomial of the product of S1, or this is also equal to the Poincare polynomial of G-dimensional complex torus, maybe up to some suit of the cohomological grading. So roughly speaking, this formula means that we are counting how many G-dimensional complex torus are there in the modular space of stable sheaves. But so here's some technical subtlety of the previous definition, because I did not explain about the choice orientations. So as in the similar to the cohomological DT invariant, the previous definition of Gopakumar-Vafa invariant may depend on choice of orientation. So in order to avoid this, we have to pick some special choice of special type of orientations, which we call it as Calabian orientation data. By definition, we say that orientation data, so this was the square root line bundle of this virtual canonical bundle. So this is called Calabian if there is a line bundle on the chirality such that this is coming from the pullback on the other heap of the char map. It is not clear yet whether we have such a Calabian orientation data in general, but in several contexts, we know that there is. And so this is one of the important question in the Gopakumar-Vafa theory, whether there is such a orientation in general. For example, in the previous case, that in the previous example, there was the example of C is a nodal actional curve, and I have this D critical locus where its reduced part is as C. And in this case, there were two choice orientations, either C or L. And in that case, the Calabian orientation is just the trivial one. So this is the Calabian orientation. So in the genus zero case, so there were the alternative definition using the usual Donaldson-Thomas invariant due to cuts. And in fact, in the genus zero case, the definition of Gopakumar-Vafa invariants is about the genus zero invariant in the previous one. That is, so this was the definition of our Gopakumar-Vafa invariant. So then, by substituting y minus 1 to this formula, then in the right hand side, by substituting this one, I get only n0 beta because for positive g, the other terms just vanishes. But for y minus 1, the left hand side is nothing but the so this is minus I chi of nothing. So then this is nothing but the Euler characteristic of the of this cohomological Donaldson-Thomas invariant. And this was nothing but the weighted Euler characteristic. This is nothing but the Donaldson-Thomas invariant. So anyway, so in the y after substituting y minus 1, we discover this formula. So this was the original definition of cuts of genus zero Gopakumar-Vafa invariant using the Donaldson-Thomas invariant. I give some example about computation of Gopakumar-Vafa invariant. This example shows some intuition of why it is not natural to consider that definitions. So let's assume that the child variety for some given choice of homology class beta is in fact consists of just L point. And each L point corresponds to smooth curves of genus GI. So the picture is that I have Calabian C for the X, and there are only L curves. And assume that it does not deform inside the Calabian C-fold, so that this is super rigid. This means that the normal bundle of this each curve has no global section. So then each curve do not deform inside X, and these are isolated quality in the moduli space. Then in this case, if we consider moduli space of one-dimensional stable sheaves of this moduli class, then this is just some line bundle supported over one of these curves. So the this is nothing but the disjoint union of the Jacobian. So this is of course isomorphic to the Jacobian of C. Sorry, so this is pic Gi of Ci. So this is isomorphic to JCi. And so anyway, so for each I, so this fiber is Gi dimensional complex torus. And this is topologically homeomorphic to the product of S1. So then but in this case, this modular space is smooth. And this vanishing cycle complex is nothing but the constant shift, up to shift. So then by applying the previous definition and also noting that just this formula, so this is nothing but the formula of the Poincare polynomial of the product of S1. So then we conclude that this NG beta is just number of the curves whose genus is equal to just G. So this gives us some innovative intuition that this one in fact counts number of curves of homology class beta and the genus is just G. But of course, there are several cases where the curve in fact moves. So I give another example. So this is the previous example about elliptic fibration. Let F be a elliptic fibration with section and integral fibers, which also appeared before. We have this one, elliptic curves. So then again, let's take beta to be the multiple of fiber class. Then here the chart map was given this way. So in this case, let's recall that this is M beta is isomorphic to X. And here beta chart map is given by these constructions. And in fact, in this case, this modular space is also smooth. And by taking the Kavli orientation, the perverse shift of vanishing cycle is nothing but the constant shift, maybe shift by 3. So then the Gopakumar-Vafa invariant can be computed from the push forward of the constant shift by these elliptic fibrations. So this is also computed easily. So the resulting computation is given in this way. So by looking at the previous definition, this first one is the genus zero Gopakumar-Vafa invariant. So this matches with the fact that it is the Euler number of the modular space up to sign. But the interesting point is that we have also genus 1. And for genus 1, so this is the Euler characteristic of the base S. So this base S is so regarded also as the chair variety is a symmetric product, but the S is the in fact the locus where the fiber of the Hilbert chair map is in fact non-empty. And S is the locus where it parameterizes genus 1 curves. So in this way, so this Euler characteristic is regarded as virtually counting the genus 1 curves inside of this modular space. So now from this, using our definition of Gopakumar-Vafa invariant, we can formulate the Gopakumar-Vafa PT and GB conjecture. And so we call that for Calabian C for the X, we have the other definitions of Gopakumar-Vafa invariants. From Gopakumar-Vafa invariant, we have this invariant. So this is a priori, this was a rational number, but this is now to be integer. From PT invariant, we can also define this one. And this one, it is was not clear whether this vanishes when G is negative, but this is now known to be a self theorem because of the Gopakumar-Vafa PT correspondence together with the vanishing of this efficiency big G. But as I said, each these theories do not directly count curves. So these are somehow defined from either Gromfit invariant or PT invariant, and then define it as some sort of transformation formula, which is so a lot of bias, but they mean a priori. So then the conjecture equality is that we have this conjecture. The point of this our definition is that on these definitions, it is a theorem that in fact, for example, in the genus in the Gromfitten side, it is a theorem that it is integer and it vanishes for sufficiently big G. So these two are the basic theorems. And from PT invariant, it was not clear for the vanishing of therefore G negative. So this is the theorem. But the what definition of this NG beta? So this is a priori integer, and from this definition, it is also 0 for sufficient big G. And of course, this is also 0 for negative G. So these conditions are automatically satisfied from the definition. These are not the theorem. So in this sense, so these are the natural properties which should be required for the direct curve counting. So in this case, this is in some sense more natural definitions. And again, so this conjecture is known to hold, as I explained in the previous lecture, for G equals 0. So this is a consequence of many things about Gromfitten PT correspondence, is vanishing, together with wolf crossing. However, this is open question for higher genus. Even for single example, this is not easy problem, and it is interesting to see this relationship. But before we have this definition, there have been several mathematical approach in defining G's invariants. In fact, so this definition follows from original proposal by Gopakumar-Vafa from some physics approach. The idea is that so they consider some ST2 product, ST2 action on some cohomology theory on the moduli space of so-called D2 planes. So first, Hosono Saito Takashi interpreted this as the action of the intersection cohomology. However, even in the genus 0, it does not match with the Gopakumar-Vafa invariant defined from Gromfitten invariants. And after there was work by Joyce and his collaborators about cohomological DT invariant, Kim and Lee also considered something similar construction, some similar construction DT perversive, and they considered this this cohomology theory. So this means that m is perversive, but not only perversive, but it in fact comes from the mixed Hodge module. So a mixed Hodge module admits weight filtration. So this group means that the associated group of the weight filtration. So the point of taking a weight filtration, weight associated group of the weight filtration is that to make it is perversive to be coming from the pure Hodge module. Which means that it has some decomposition after pushing forward by proper maps. As that is the Bernstein-Ring decomposition theorem holds. So this one also holds from this one. So this is the cohomology theory of the intersection complex. This is also coming from the Pierre-Hodge module. So it also admits the decomposition theorem. So in our approach, so we don't know whether such a decomposition, so we don't know whether there is some SL2 product to action. But we expect that there is. And our definition is some kind of shadow of the such an action. Assuming the existence of such action, our definition is in fact agree with the one coming from these actions. But I'm explaining how this V-algebra action is relative to the Gopakumar-Vafa invariants. Let's recall about SL2 representations. It's because that this V-algebra SL2 is generated by 3 elements equals 0, 1, 0, 0, F equals 0, 0, 1, 0, and H is of this one. And this satisfies this relationship. And also for each half integer, there is irreducible representation of SL2 with dimension 2j plus 1, which is spanned by this element. There is some element of this representation so that this irreducible representation is spanned by this element and also elements applying this element E to 2j times. And after a composition of 2j plus 1 times, it becomes 0. And the action of H is given in this way. And the action of F is given using these relations and these actions and also using this relationship. So then there is some SL2 representation coming from the cohomology theory. So this is coming from the hardware theorem. For a smooth projective variety M and also with ample divisor HM, we have the intersection complex. So in this case, this is just simply the QM shift by dimension M. So this is of course perverse sheaf. In this case, the intersection cohomology is just the shifted cohomology. And it admits natural SL2 action, such that the its action of E is given by H product of this ample divisor. So it sends IHJ to IHJ plus 2. I'm sorry, so this action is not there, but HH. The action of H is given by multiplication of the degree, and the action of F is given by using the divisions of E, H, and F. And in particular, if A is a abelian variety of dimension G, then in fact, so this is representation is independent of the choice of ample divisor. And in the case A is a abelian variety of dimension G, then this is described in terms of the previous irreducible representation in this way. So in fact, for example, G equals 1 case, this is elliptic curve, and the intersection cohomology of the elliptic curve is, so this is Q plus Q2 plus Q. So this is the H0 of E, H1, and H3. So by taking the wedge product of the ample divisor, we have the isomoism between this one and this one. So this gives the representation 1 over 2. And this middle part, so this one gives the representation of 2, 0. So in this way, so in the G equal 1, get this presentation. And in the for D-dimensional case, This is just take the tensor product G times. So this is the important representation. And then that was the SL2 representation, but we also have the SL2 product, SL2 representation. If there is a projective variety M together with the projective morphism to other projective scheme B. So in this case, we have the Bernstein-Bernstein-Dwyer decomposition of the push forward of the IC shift to the cohomology, direct sum of its shifted cohomologies. Of course, in this case, so I didn't define ICM, but when M is smooth, so this is nothing but the this is not QM shifted by dimension M. But the point is that in in this case, this is coming from the pure cohomology, so it can be we have such a decomposition theorem. So then, if there is such a decomposition, then by taking the hypercohomology, we also get the decomposition of this cohomology into the cohomology over A over B. So this is now bi-graded. So this is just coming from this decomposition and after applying the hypercohomologies. So then we have two operators. So if there is no morphism, I only have SL2 representation given by just this wedge product of HM. But there is also ample divisor HB on the base. And in this case, we also have another representation just coming from the wedge product of HB. And just something similar homomorphism in the previous slide. So these two actions defines SL2 product, SL2 action. So this notation means that this is left action. And this notation means this is right action. So then, now this is SL2 product, SL2 representation. But because that SL2 representation, the judicial representations are classified by each half integers. But then we can formally write this judicial representation in this way. So more precisely, we consider it as element in the Grothendieck group of SL2 product, SL2 representation, and then write it in this way. The point is that if we consider the Grothendieck group of SL2 representations, it is spanned by these representations. But at the same time, this is also spanned by these representations coming from the cohomology of the abelian varieties of dimension G. So this can be easily shown from the fact that IG is 2 times over 2G. Yeah, so maybe, yes. So then we can define that. So now RG is some virtual SL2 representation. This means that RG is virtually eaten by some linear combination of judicial representation. And then take the dimension of the alternating sum. So then this is how we get some number from the SL2 product SL2 representation. So this was the original approach from the Gopakumar-Vafa, and in their paper they assume that the implicitly assume that the modular space is smooth, and in that case, we have this SL2 product, SL2 representation, and then get this number using these representations. Then here is a relationship between this number from the SL2 product SL2 representation and Gopakumar-Vafa invariant. Our definition was that by pushing forward, our definition was not pushing forward ICM, but it was vanishing cycles. But if when M is smooth, then phi M is in fact isomorphic equal to QM dimension M, maybe up to some choice orientations, if M is smooth. So far, I assumed that this M is smooth. And in this case, the NG is nothing but NG defined by this one appears as a coefficient of writing it in this way. So this is nothing but the formula which appeared in our definition of the Gopakumar-Vafa invariant. So then, as I said, so if so that was a more general situation, but if we apply it to the Hilbert chair map from the modular space one-dimensional shapes to the chair variety, if M beta is smooth, then our invariant which appeared, our invariant was in of chi of I pi star phi M. So this one is so this one agrees with the invariant defined through SS product SS action. So yes, so this is okay when the modular space is smooth. So when modular space is smooth, yeah, everything works. So in the case of M is smooth, so we have SS product SS action, and our definition agrees with the invariant defined through this rearrangement action. However, if M is singular, it is not clear whether we have the SS product SS action on this cohomological DT invariant. We expect that there is such an action, but it should require some more detailed analysis of the Hilbert chair map. This is because this is coming from the pure, this is coming from mixed Hodge module, but it's not necessarily pure. So it is not clear whether we have the decomposition theorem. But nevertheless, we expect that so locally this Hilbert chair map is given by some special type of critical locus descriptions, which we call it as strictly Cavalier critical chart. And in that case, there is some decomposition of this Perverse of phi M pushed forward by this Hilbert chair map. But this is a conjecture, and this is quite a difficult one. But nevertheless, our definition of this one is well defined without using such SS2 product SS2 action. So that is why we define in this way. And the and previously the Hosono, Saito, Takahashi, and Kim Lee, so they defined the GV invariants using these cohomology theories. In their cohomology theory, so this is the cohomology of the intersection complex. So this is pure. And in Kim Lee, so they take the weight filtration and its associated gradient. So this is pure. So this there are some SS product SS actions. But unfortunately, their definition do not agree with the Gopakumar-Vafa invariant defined from the Gromfit invariant. If M is singular. So anyways, when M is smooth, everything is okay. So every definition, so Saito, Takashi, Kim Lee, and our definition agrees when M is smooth. The issue has been what was the definition when M is singular, and what is the cohomology theory we should consider. And so far, so the existence by CO2 product extraction relied on the decomposition theorem. So in order to have this decomposition theorem, the perverse sheaf must be coming from pure Fauci module. But in your definition, it is observed that considering the vanishing cycle sheaf, which is not necessarily pure, is important because it is important to keep track of the extensions of which the weight filtrations. Then I explain one more important aspect of the Gopakumar-Vafa invariant, that is chi-independence conjecture. So I already discussed about chi-independence in the genus zero, and we also expect something similar in the higher genus. We defined the Gopakumar-Vafa invariant from the modular space of stable sheaves of this Chern character. So this is Chern character. And so this last number chi equal 1. So this is chi f equal 1. So this is just a conventional reason because if I take chi equal 1, the modular space is in fact fine modular space. So there is no strictly semi-stable 1, and there is a universal sheaf, and also so there is also one more thing. So this is in fact independent of a choice of ample divisor H. So this chi equal 1 gives several mathematically good properties of this modular space. However, from a physics point of view, there is no reason that we should take chi equal 1. So there should be no meaning about this choice. And so it is more natural to consider arbitrary choice of chi, and then define the Gopakumar-Vafa invariant, and then finally it should be independent of this choice of chi. So that is the ideal story. And in fact, for G equals 0, so there was a definition of this invariant and 0 beta chi. So this was defined using the generalized DT invariant. So let's recall that it is given by 0 beta chi. So this was a rational number, and then this is defined to be of this multiple cover formula. A priori, so this is a rational number, but it can be shown to be in fact integer. And this is a deep theorem that it is independent of choice of chi. And as I explained in the previous lecture, this independence of chi is a consequence of many big results, Witten, PT, correspondence, and the vanishing of Gopakumar-Vafa invariant in Witten side, and so on. And also wall crossing formula. Anyway, consequently, we know this one, but this chi independence, so this is purely sheaf theoretic statement, and it is desirable to have a purely sheaf theoretic proof for this chi independence. So now I'm going to formulate about chi independence for higher genus. So now let's consider inverter chi. So this is a good modular space of semi-stable sheaves. This is a projective scheme. But for chi is not one, this modular space is not necessarily fine modular space. So instead we have the modular stack. So this is a modular stack. And it's good, this is a good modular space. So when chi equal 1, this is fine. This means that chi equal 1, this modular stack is in fact the trivial C-star job. But when chi is not 1, this is a more complicated stack. But anyway, I explained about the construction of DT perverse sheaf. And So there is also construction of DT power sheaf for the modular stack rather than modular space. So this is also the marked by BBBBJ. So this is then we have the vanishing cycle complex of this modular stack. So then I define another power sheaf of this got modular space using this power sheaf. So this is defined to be first take the push forward of this DT power sheaf to the good modular space, and then take the first perverse cohomology. So this gives the power sheaf on here. So the appearance of the first cohomology is related to this, the GM jab structure. In the Kaiko 1 case, this is the same as the DT power sheaf. But when Kaiko not 1, this is different from the BT power sheaf because the DT power sheaf is anyway lives in the stack. And if this is good modular space, there is no construction of the BP power sheaf at the strictly semi-stable point. But nevertheless, also the DT power sheaf lives in the stack, and then push forward it, and then take its first cohomology. So then this is the definition of the so-called BPS sheaf. This BPS sheaf is some global version of the similar construction due to Davidson and Myhart. So in their paper, they construct such BPS sheaf and BPS cohomology. In the case of quiver with potential, so I did not explain about anything about quiver or potential, but anyway, quiver is the oriented graph. And the symmetric quiver means that the number of arrows from one vertex to other vertex is the same in the opposite order. So for example, this is symmetric quiver, and then potential is certain the sum of the cycles of these paths. So then starting from this quiver with potential, and also its dimension vector, we have the modular stack of Q representations. It's a good modular space. So anyway, so this is given by certain quotient stack, and this is given by this GRT quotient. So this is smooth stack, and this is singular stack. And the superpotential induces a function on the good modular space. And by composing it, we also have the function of this smooth stack. I also denote it as trace W. So then the Davidson-Myhart BPS sheaf is defined by the applying the intersection complex of this polarity to these vanishing cycles. But here, now this is singular in general. So this intersection complex is defined from the constant sheaf of the sheaf. So this is more complicated one. But anyway, so there is such a definition. So this is the smallest extension of the constant sheaf to the singular locus as a power sheaf. Then this is the result by so-called PBW theorem in their cohomological mass autonomous theory for quiver with potential, that this BPS sheaf is in fact isomorphic to the first perverse cohomology of the vanishing cycle complex over here and pushing forward by this up P. And in fact, we have this the modular stack. So this is the modular stack and the good modular space. And this map is analytic locally approximated by this quiver situation. So at each point of this one, we can construct some quiver Q and also potential such that this map is analytic locally isomorphic to this one. So in this way, this BPS sheaf in the previous slide gives a global version of the BPS sheaf of Davidson and Myhart. So then using this BPS sheaf, I can formulate the chi-independence conjecture. Let's return to the situation of Calabian threefold. So X is a Calabian threefold, and we have this moduli space of one-dimensional stable sheaves. And I have the Hilbert charm map. And also we call the BPS sheaf phi m, which lives in here. And then let's consider this one. So this is when chi equal 1, this is the one which appeared in the definition of the Gopakumar-Vafa invariant. Then the conjecture is that this, so this is in fact a low ramp polynomial, but this is independent of, sorry, this is a theorem. The theorem is that, so this is independent of the choice of amp divisor. So this is the bias in the case of chi equal 1, but this is non-trivial when the h is when chi is not 1, because m beta chi h depends on h. If chi is not 1. And yes, this is one of some sort of word crossing of this sort of invariant. Then the chi-independence conjecture is this. So this low-ramp polynomial defined from this BPS sheaf is independent of chi. Then assuming this chi-independence, we define NG beta chi just by this same formula as in the definition of Gopakumar-Vafa invariant. Then the chi-independence conjecture means that this energy beta chi is independent of chi. So in fact, this is equal to the energy beta in the previous definition. Of course, in this notation, energy beta was energy beta and chi equal 1. So chi independence means that this one is in fact equal to the energy beta. And for the G equal 0 case, the energy beta chi, so this was originally defined using the generalized ET invariant, but it also coincides with the one defined using the BPS sheaf. And recently, there are several activities of proving this chi-independence conjecture. For example, in the paper by Marek and Shen, they proved the chi-independence conjecture in the case of total space of canonical line boundary for toric repeat surface. And the curve class beta is an ample class. So the point is that they proved this chi-independence purely from the sheaf theoretic argument. So the proof is also interesting. So they use the generalization of the ingold support theorem. That is, roughly speaking, it gives the information of the support of the push forward of the constant sheaf for some morphisms called some weak linear vibrations. And this kind of statement plays a crucial role in the proof of a fundamental lemma of the Lagrange program. So it is interesting to see that so this kind of support theorem has some interaction with this Gopakumar-Vafa theory. And using the work by Monique and Shen, so there is also result by Kincho and Koseki. So the chi-independence conjecture is true in the case that X is the total space of length vector bundle over smooth projective curve, whose determinant is isomorphic to omega c. So this condition is nothing but the X is just a Calabian threefold. So the difference from the previous work by Monique Shen is that in the case of X equal total space of canonical bundle over some derivative surface, the moduli space of one-dimensional stable sheaves, this is smooth. In fact, so this is just isomorphic to the moduli space of stable sheaves on the surface S itself. And because of the derivative condition, this is smooth. But in this context, the moduli space is not smooth, not necessarily smooth. So we have to consider the vanishing cycle complex to consider the Gopakumar-Vafa invariant. Here, in this case, because whether it's smooth, it is enough to consider constant sheaf. But here, we need the vanishing cycle complex. And in fact, the difficulty of dealing with Gopakumar-Vafa invariant is that the vanishing cycle complex is somehow gluing of the locally defined one. But if there is some global critical locus description, then it may be possible to show that the DT purple sheaf is the global vanishing cycle complex. In fact, what Kinjo must have proved that in this case, the moduli space of stable sheaf is globally written as some critical locus of some function. And in fact, this smooth ambient space is also given by some moduli space of stable sheaves on the total space of line boundaries where the degree is sufficiently big. So this is regarded as some funnel surface, the tapered surface. So then applying the argument of Mauryk and Chen. So by Mauryk-Chen's argument, we have the kind dependence on this space. And then applying the vanishing cycle factor for this function f. Then we get the kind independence. So that was the strategy by Kinjo and Koseki. But so these are the non-compact caviar seafood cases. But so it is still conjecture about the kind dependence is still conjecture for more general caviar seafood. So now finally I've explained the current status about PT and Gopakumar-Vafa conjectures. So first, this example was also written in my paper with Mauryk. So let S be any case surface and is elliptic curve. Any case surface is so this is a free Jitsu quotient of some KC surface. We have the universal covering space is a KC surface. Until we take a caviar seafood given by the product of this KC surface and the elliptic curve, and then take a quotient of this involution. This involution is acts on Studer by this covering involution, and it acts on elliptic curve by x to minus x. Then any case surface S always admits some elliptic fibration, but it may admit some the non-reduced fibers. So S to P1 with some non-reduced fibers. Then the reduced fiber is some twice of some curve. And then let's take a curve class given this way. So then these are the consequences of the computation of the Gopakumar-Vafa invariant. So this is interesting because it gives also counterexample to the original previous definitions by Hosono Saito Takashi and Kim and Lee. Let's assume that the for double curve it is of type IN. So this is a circle of P1, like this. She is like this one. So there are n P1. So the moduli space of any case surface is connected. So the this means that if the Gopakumar-Vafa invariant can be defined, it should be deformation invariant. So the resulting invariant should be independent of the number of the degenerate rational curves. In fact, by comparing the previous Saito Takashi and Kim Lee and our definitions, and also the expected answers, that is from meeting or PT theory. So then the Saito Takashi and Kim Lee, so they depend on a choice of n, but in our definition, so this is independent of n. And the expected answers are also the same. So this gives evidence, and this is also gives a counterexample about this Kim Lee constructions. So this is a picture of the Hilbert map in the previous definition. So this exact picture shows that how the Hilbert map is complicated or behaves not good. That is. So this is a picture when n equals 2. That is when the degenerate fiber is like this. But generically, for any case surface, the W cover is W of the elliptic curve. And in that case, the Chair is just a 4 point. If you deform the any case surface, so that the non-rigid fiber becomes like this. Then the Hilbert chain map looks like more complicated. So we have this picture. So this the base is the chain variety, the image of the chain variety, and this one is the modular space of the stable sheaves. So at this point we have some critical locus differentiation. We have the critical locus of x, y, d, or something like this. So next, I explain some more general result in the case of irreducible curve classes. By definition, a curve class on curve C4 is called irreducible if it is not the sum of the classes. So this means that for each irreducible curve class, corresponding one cycle is always irreducible. So I don't have something like this. So then this conjecture can be just simplified to like this. In fact, this is the generalization of the well-known formula, which gives a relationship between the Euler characteristic of the symmetric product of curves and also the Poincare polynomial of its Jacobian. So each one can be directly computed. But in the case of Poincare polynomial of Jacobian, because Jacobian is homomorphic to the product of S1 to G, and the Poincare polynomial of S1 is just 1 minus Q. So it is given 1 minus Q over 2G. And then take quotient by this one, get this one. For the symmetric product of curves, for example, in the circle P1, sim n P1 is just Pn. Euler characteristic of Pn is n plus 1. If you consider it generating series, it is like 1 plus q plus 2q square plus so on. So this is equal to 1 minus q over 1. 1 minus plus 3. So then this is a general result in the case of local surface. So let S be a smooth projective surface with h1 s equals 0 and x is total space of canonical bundle. Yes. Maybe I think I forgot to say that the definition of the Vafa invariants also works where x is not projective. So that the definition also makes sense for non-compact curvature symbol. Then the PTGV correspondence conjecture, this is true for any irreducible curve class. So that is, we have this formula. So that was our theorem with Tabeshmavic. Here is the brief idea of the proof. So first, for a given element of the Char variety, so this is now irreducible curve inside the curvature C-fold. I take the Barsa deformation. Barsa deformation means that this is the deformation of the curves, but allowing deformation of C not outside of the curve X, not outside of X. So this is a deformation of the curve itself. So not deformation inside of the variety X. So this also includes the smoothing of this curve C. So then let's take the yes. Sorry, this is pi t. Let's consider the pi t relative Hilbert scheme of endpoint. So this is a relative Hilbert scheme of endpoint, and this is a relative rank 1 total free sheaves with Euler characteristic 1. So on the generic fiber, this is smooth. That is CT smooth for generic T. And the generic fiber, this one is just a symmetric product of the smooth curves, and also the Jacobi of this one. But for the generically, so the correspondence is the one which I explained. That is the Euler characteristic of the symmetric product and the Poincare polynomial of the Jacobian. But this correspondence can be extended to the singular fibers by considering the IC complex of Cn and push forward, and also the IC complex of this one here. In fact, so these are in fact smooth. So these are the constant shift, up to shift. So this is this formula. So this gives a generalization of the formula in the case of smooth one, and that was proven by Moik-Yuan and Miglioni and Shende. Now the point is that I have this picture, and the point is to construct some function g such that it's by taking its composition, this critical locus recovers the PT moduli space and the moduli space of stable pairs, stable shifts. So then by applying the vanishing cycle factor of phi g to the previous formula, so apply phi g to this formula. And use the fact that the vanishing cycle factor preserves perverse T structure and also the proper push forward gives the formula for the PT and GV correspondence. So finally, so I explain about this, the latest result in this direction. So this is due to Davis and Koseki. So so this is the result for the non-primitive curve class. So in the previous slide, so that was only irreducible curve class, but the computation of the Gopakumar-Vafa invariant is more and more difficult when the curve class is not primitive. So that it is some multiple of the effective curve class. So in this case, they computed Gopakumar-Vafa invariant in the case of total space of ranked bundle. So they use also the machine learning developed by Kinjo Masuda and Kinjo Koseki about the independence. Anyway, so they computed the Gopakumar-Vafa invariant for the curve class twice of this curve class. This is non-primitive. And they calculated in this way. So this is quite remarkable because so this is very difficult to compute, and the computation is quite non-trivial. And in fact, it matches with the Gopakumar-Vafa invariant defined from either Gromov-Hitten or PT invariant. So yeah, so this is the latest result in this direction. And there are several other results and conjectures which appeared. But anyway, so here I give some summary of some open questions, other directions. First, I defined this Gopakumar-Vafa invariant, but this is defined through the vanishing cycles, not vanishing cycles. So it is not clear yet whether it is deformation invariant or not. So this is one of the foundational questions. And we have to see more precise understanding of the Hilbert chair map. So we expect that there is some D-critical chart that is locally on the chair variety. So that is one of the maybe the difficult and important question. And for this, I think we have to know more about the chair variety. So this is quite mysterious moduli space. Also, the existence of Kavli orientation data. So this is also not yet known. The existence of this algebra action. This is also important from the physics point of view. So if this is pure, then there is such action, but this is not necessarily pure. And so in order to have this action, I think this second question is quite important to see. Also, independence conjecture. So this is conjecture in many cases. And I think this is also interesting question that from our definition, it is known that this is zero for sufficiently big G, but it is not clear what is the explicit choice of G beta. So there are recent work by Liu on from the PT side. He gives some optimal band for such G beta using the BMT inequality conjecture for Kavli seaports or for P3 by projections. It is also interesting to see such a bound from this definition directly. So there are also some works about refined Gopakumar-Vafa invariant. That is, in the definition of Gopakumar-Vafa invariant, we take the Euler characteristic over the base position chair variety. But it is also interesting to see such invariant without taking the order characteristic. So there are works by Lidian Zhao and Konoho physician in this direction in the case of Loka-P2. And of course, this PTGV correspondence is, so this is the most difficult conjecture. And so in recent years, I was working in the categorification of the Thomas invariant. So in this lecture, I didn't talk about anything about this. But this should be the more interesting direction of the research. Categorification means that, in fact, you really consider some DG category, which we covered this invariant. So it will also satisfy some symmetries and also interesting structures. Okay, so yeah, I stop here. Thank you very much.